All right. Hello, everyone, and let's get it recording. It might be the better thing to do first.
Recording in progress.
All right. Hello, everyone, and welcome back. We are continuing on with our MCT4C course. This is the Math for College Technology. We are on lesson, or I should say, start of Unit 3, and this is lesson 11. So we're over halfway done the course. The first few lessons of the course take longer to go through than the other lessons. So Unit 3 is actually quite quick to go through. So it's just going to be one day for each one. And so let's have a look. Today I have the Desmos scientific calculator as well as the Desmos graphing calculator. I will likely not need either, but it is useful to show what these things look like. So we're going to be having a look at the vertical displacement, something called the amplitude, which we saw earlier, determining the max and min from a graph, as well as something called a phase shift, which we call horizontal translation. And we know things are going well if we are able to graph the sine and cosine functions and describe their properties, and graph transformations of the sine and cosine functions using their base graphs. And so essentially for today, we're looking at variations of, say, a sine of theta minus p plus q, or if you prefer, a cosine of theta minus p plus, I should say plus or minus q, but in reality, if q is positive or negative, it will take that corresponding sign. And note that these parameters, a, p, and q, correspond to the amplitude, the vertical displacement, as well as the phase shift or horizontal translation. So if you remember from yonder years, previously you might have studied transformation of quadratics, where if you had, say, a base function for a quadratic, y equals x squared, you learned about some transformations of the form y is equal to x minus h squared plus k. The letters may differ depending on where you would have learned these from, but they essentially mean the same thing, where we have a parabola that was transformed in some way, either stretched or compressed vertically, and then perhaps reflected in the x-axis, and then shifted around by h and k units. And that's exactly what we're going to be doing here. And so first thing we're going to look at is the vertical displacement of the sine and cosine functions. And when I say sine and cosine, I mean we're going to just interchange which one we talk about, since what applies to one will apply to the other. The only thing that will change is the initial starting position will be different. So the concept of a vertical displacement is the shifting of the sine or cosine either directly up or directly down. And so we can use a lot of letters here. This course happens to use the letter Q. So Q is used to represent any shifting up or down of the sine or cosine function. So suppose you have f of theta is equal to sine theta plus or minus q, and you want to compare, say, f to g. G of theta is defined to be sine theta plus 7. So all that means is for each value of sine theta, we shift the function upwards 7 units. Seems simple enough. Let's see what this looks like. And again, I sketched out this one in the interest of time, but we'll go ahead and study this on our own afterwards to see how we do this. So for example one, suppose we're interested in the vertical displacement for the sine function, and we're going to describe the effect on the sine function when q is equal to positive 2. And so for our solution for this, f of theta equals sine theta, the graph of f of theta equals sine theta shifted upwards 2 units to become g of theta is equal to sine theta plus 2. So all we do is take the graph of sine theta and add 2 units to each y value. Okay, and so here's what the graph of this looks like. And so here I will darken this in red for us. Here is the original sine theta function on the interval. The graph here I show has 2 cycles, but we can just have a look at the cycle between 0 and 2 pi. And again, for if you need the extra reminder, we can also think about this in terms of 0 to 360 degrees. The graph of these will be identical. Okay, just depends on whether you're using degrees or sine. And all we do is we take each of our 5 important values, that is the 3 zeros, as well as the max, and we drag those up 2 units. So notice here that the max is at 1, and we go up 2 units. Sure, I should say plus 2 units upward, and we arrive at that value. And all we do is take each of these values and drag them up 2 units on our scale. Notice that our scale is, you can see our scale for the y-axis below here. Okay, that's it. That's pretty straightforward. And so the way to do this is we want to sketch the base function. So in terms of steps, sketch the base function. And so this will be sine theta or cosine theta, and then just apply the transformation. Okay, and so let's have a look up and see what this means for us. So we're going to have a look at the vertical displacement for cosine function. So describe the effect on cosine function when q equals -3. So if we have, say, f of theta equals cosine theta, then we're interested in the transform function g of theta, which is equal to cosine theta subtract 3. And the reason why I distinguish between f of theta and g of theta is so that we just understand that these are two different things. There is nothing wrong with calling this f of theta equals cosine theta and f of theta equals cosine theta minus 3, except that we run into ambiguity problems where traditionally we know that f of theta is used to represent a general function, but typically when we have a transform function, we just use a different letter because it's easier. And usually different letters are, say, g of theta or h of theta are the other two most common letters we tend to use to denote function notation. So we could say that these are the same as, so I should say, same meaning as f of theta, although they're not identical. Okay, so what's the effect? So this is going to be a vertical displacement down 3 units. That's quite the sentence. So we can also call this a vertical displacement down 3 using just shorthand notation like such. And so I'm only going to sketch one cycle of this. And so I did up a graph for us already. And so there's our scale for what goes from +1 to -4. And let's say every fourth unit we'll call 90 degrees. So this will be pi on 2. This will be pi. This will be 3 pi on 2. And this will be 2 pi. And again, these are just the standard units that I use. Okay, so if I want to sketch cosine theta, I can do that. Cos of 0 is 1. Cos of pi on 2 is 0. Cos of pi is -1. Cos of 3 pi on 2 is 0. And cos of 2 pi is 1. And so I can connect these then with a smooth curve, like so. And we can put little arrows on it to show that this continues on. And this is my generic function, f of theta equals cosine theta. So to sketch the transform function, all we need to do is to take each of these 5 points, the 2 maxes, the minimum, and the zeros, and drag those down each 3 units. So for for this one here, we go down 1, 2, 3 units. For cos of pi on 2, we go down 1, 2, 3 units. For cos of pi, we go down 1, 2, 3 units. For cos of 3 pi, the same, and cos of 2 pi, the last. If we so need to, you can also type this into the equation. So you could make a table of values to help you do this. So here's, say, cos of theta minus 3. And you would choose the regular values we know from before. Note that this won't always help you, but for this one it will. And we can just type this in. So for example, we could type in cos of pi minus 3 radians, and we can see that we get an answer of -4. And we can vary what our solutions here, or vary our theta values, and see what the corresponding answers are going to be. Let's type in cos of pi over 2. There's our -3. And cos of 3 pi over 2 is -3. And so we can then connect this with a smooth curve as best you can. And we claim that this is g of theta, which is equal to cosine theta minus 3. And again, it is proper to go ahead and label your graphs just so that way we know what we're talking about. Okay, so sketching this pretty straightforward. It's just a vertical displacement down of the cosine wave function by -3 units on each of the 5 points. Okay. And a graph of this can also confirm. So if we want to make sure in radians, we can type in cosine, we'll use x, but it's the same thing. And we can also type in cosine of x minus 3. And you can see we get the exact same function, 3 units slower. So you can see cos of pi -1 corresponds to the base function. Cos of pi comma -4 corresponds to the transform function. I won't belabor this point too much, except to say that you can use Desmos to verify this, as well as what we know about when we graph this with respect to previously with quadratic functions. Okay, let's continue on. So we can also stretch or compress a periodic function. However, in the case of quadratics, we said it was a stretch or compression. Here, when we talk about stretch or compression, we say that this is going to affect the amplitude. So the letters A is used to stretch or compress the function y equals a of sine theta, or of course, y is equal to a cosine theta, either one. If a is between 0 and 1, the function is compressed by that factor of a. When a is greater than 1, the function is stretched or expanded by a factor of a. And when a is less than 0, the function is then reflected in the x-axis. It's worth noting that then you'd run into the situation where if a happens between -1 and 0, this is going to be also a compression. And if a is less than -1, this will be a stretch. And note that the amplitude is going to affect y values. Okay, so let's see this in work. So the amplitude is the maximum displacement from a reference line in either the positive or negative direction. Well, okay, what's a reference line? So the reference line was this middle of the function. So I mentioned earlier, let's not work in this color. Let's work in blue. The very middle of the function is what we call the reference line. So that's the point where it's the middle way between going up going up and going down. Okay, so this is what we call the reference line. This also has another name. It's called the equation of the axis. It's got a lot of different names, but they all mean the same thing. And it just refers to the middle point between the max and the min. And so the textbook uses the term max to represent the maximum value. They will also use the letter here, capital M, and they use the word, and we'll use the word min to represent the minimum, and they use little m to represent the minimum. I don't like the ambiguity between capital M and little m, but just note that it is fairly standard to say that the max is capital, the minimum is the lowercase value, and so forth. So if max represents the max value of a periodic function on a cycle, and min represents the minimum value, then the amplitude A is equal to max minus min divided by 2. And we saw this from earlier. Okay, so if we were interested in the amplitude of the sine function, so suppose we were given the equation f of theta is equal to 3 sine theta, what does this look like? Well, in terms of a graph, and the textbook uses this kind of scale. So instead of writing exact values, they write these in decimal notation. So note that this maximum up here happens to be pi over 2. And so if you take pi and divide it by 2, this is the decimal version. So this will be that 1.57. The x-axis is pi, which is going to be exactly 3.14. The minimum is going to be 3 pi over 2, which is going to be 4.71. And then you can't see it here, but there's going to be the end of the cycle, which is going to be 2 pi, which is going to be 6.28. So the textbook commonly converts these all to decimals. You can do that as well. I find it easier to think about this in terms of pi, but again, I leave that decision to you. And so what does it look like when we graph f of theta is equal to 3 sine theta? So we know that the amplitude will be equal to 3. This is verified by the graph of this thing. If I graph what the sine theta looks like, instead of going up to a maximum of, say, 1, we now go up to a maximum of 3. So the 3 causes the max or min values to extend to that high number instead. Or what this means is you can multiply each of the y values by 3 to get to that number. We do have an example of this coming up, and so just so we can see what this looks like. We do have a detailed note, though. We should mention that the amplitude of the function f of theta is 3 equals 3 sine theta is 3. The value of the amplitude is defined as, and this is what we call the absolute value of A. Okay, so as a recall, you may or may not have heard of this before. The absolute value of -3 is the same thing as the absolute value of 3, which is 3, meaning that the amplitude is always positive, but we can have a reflection in the x-axis. The absolute value of -3 is equal to 3 is read as the absolute value of -3 is 3. And in terms of, in case you are wondering, a definition, what this means in terms of a physical representation is, I'll do a little note for us here. And again, this is a tiny addendum, like we don't need it for the course except when we talk about amplitude. Let's consider the number line is actually the best way to think about this. If there's people in a class in front of me, I would also use that, but again, that's okay. So suppose we are interested in 2 points here, 3 and -3. So the question becomes, how far from 0 is 3? And we would say that that is 3 units away. How far from 0 is -3? And the answer is, as you might have guessed, not -3 units, but 3 units. That distance is still 3 units. And so when we read the absolute bar, this is also read as the magnitude, or perhaps another way to think about this is the distance. And you can't have a negative measurement. So if you're trying to cut a piece of wood and you need to cut off, say, a quarter of an inch, well, you need to cut off a quarter of an inch. It wouldn't be, say, cut off -1/4. You'd be like, no, I need to make sure it's a quarter of an inch longer or a quarter of an inch shorter. If it's longer, you got a problem, but alas, I digress. So the absolute value is always the positive version of that number. This is exemplified in example 4, where we wish to just determine the amplitude. This is a simple 1-mark question. Determine the amplitude of the given function. G of x is equal to -5 of sine x. So the amplitude will be equal to the absolute value of -5, and so it's going to be 5. Okay? You could also just write this as the absolute value is equal to 5. If I had, say, a question like h of x is equal to -10 cosine x, then the amplitude would just be 10. Okay, always take the positive version of whatever's in front of the sine or cos, and that's understood to be the amplitude. We would not say -10. That would be a concept error, or -5. That's a concept error that you would get wrong. There are no marks for that. Okay, let us continue. Suppose we wanted to, so we're going to graph the amplitude and a reflection in the x-axis. So we're going to graph the effect of a is equal to -0.6 on the function f of theta is equal to sine theta. Note that this notation is okay because we're saying the a value happens to be 0.6, but it's understood that the amplitude is equal to 0.6. Minor distinction, but again, worth noting. So for g of theta is equal to -0.6 sine theta, the graph will have a reflection in the x-axis, meaning that it's inverted, or this, what we call this, a reflection across the x-axis. It says it here, but again, it's worth noting that's the case. And then it's compressed by a factor of a. And so we know that, as a small note, sine of theta is equal to 1. So we're talking about -0.6 times sine of pi over 2, which is going to be -0.6. And so at theta equals pi on 2, the y value is multiplied by -0.6 to account for the change in a. And so what happens here? So in red, this is the normal f of theta equals sine theta graph. So we know we go up, passes through pi on 2 normally, passes through pi. At 3 pi on 2, passes through 1. And at 2 pi, it passes through 0. The major changes here that happen are that when we have a look at the graph, g of theta is equal to -0.6. We take the y value at 1, multiply it by -0.6, and we get this value below. Instead of a maximum, we now have a minimum. Concurrently, when we have a look at 3 pi over 2, when evaluated for sine, sine of 3 pi over 2 is -1, and when multiplied by -0.6 gives you positive 0.6. So that becomes the new max. And so we have a graph that will take on this shape. And again, this continues forever in both directions. Now, as a note, it's the x-intercepts actually remain the same, or the theta intercepts in this case, because if you take 0 and times it by any value, you get 0. Hence, these will be the same. And so we end up with just a reflection across the x-axis. Okay, I drew some of these graphs in because we have a lot of notes to go through today, and I didn't want to rush, and also wanted to make sure that we had a full solution for us. Okay, so now I'm going to graph one for us. So the textbook has a lot of questions like this. Graph the function, and we're going to graph each set of functions on the same grid. So we're going to graph f of theta equals cosine theta, f of theta is equal to 2 cos theta, and f of theta is equal to -3 cos theta. And again, I use this notation because that's what the book uses. In reality, you should call this g of theta and h of theta, so that way it's more clear to the observer, but alas, here we are. Okay, so the first one was done for us. Here they graphed f of theta equals cosine theta. So if we were to graph the 5 important points, there they are. And we're going to go ahead and label this f of theta is equal to cosine theta. And we'll just color this in red so that we're ultra clear about the graph that we're talking about. Okay. If you're ever not sure about what this looks like, feel free to go back to class 18 or lesson 10 where we studied how to graph these things. You can also use Desmos to help verify this is the case. So if I switch this to a step of pi over 2, and I zoom in a bit, okay, the red one here in our function refers to what that graph of cos theta looks like. So you can see those are our values that we care about. Now, for f of theta equals 2 cos theta, let's graph this in light green. All this means is we take our maximum and our minimum values and multiply them by 2. Take max and min and multiply by 2. Okay, so if we take 1 times 2, 2. If I take negative 1 times 2, negative 2. If I take negative 1 times 2, negative 2. 0 times negative 2 is 0. 0 times 2 is 0, and 0 times 2 is 0. And with that, we can just connect these together. And again, you just try to connect these as best you can. There we go. And so here, I put this in green. This is going to be f of theta is equal to 2 cosine of theta. That's it. And when I take the max or min and multiply by 2, this, of course, I mean for the y values. Okay, let's have a look at the last one. F of theta equals negative 3 cos theta. So we do the same thing. We're going to take max and min and multiply by negative 3. And this will affect the y values. So notice that we have a negative value here. So this is going to be a stretch, or we should be a bit more accurate and call this a vertical stretch. And we also have a reflection in the x-axis. So that's what we have. That's the transformation. If we were to actually graph what this looks like, all we do is we take the base function 1, multiply it by negative 3. We get this value below. And if I were to take 2 and multiply it by negative 3, you get 3, which actually goes all the way up to 6. So it's going to be some point way up there. And, no, sorry, I was reading the wrong value. If we take the negative 1 and multiply it by 3, we get positive 3. And on the base function, if we take cos of negative pi, which is to negative 1, and multiply it by 3, we go up to 3. And so we go ahead and connect these as best we can. This is kind of long, so I have my worry about sketching this accurately. That's not so bad. And so this is going to be our function f of theta is equal to negative 3 cosine of theta. So we can see we stretched what it looks like. We can use Desmos to help confirm this is the case. So if I have a look at 2 cosine of x and negative 3 cosine of x, and I'll go ahead and label this. Nope, not getting it off purple. There it is. You can see that between negative pi and pi, we have the same graph shown below. And if you want to as well, you can put little arrows on to extend it. But this graph only cared about values between negative pi and pi, which is what we've listed here. So there we go. All right, let's continue on. As a quick refresher, some of the questions in this one ask about determine the max, the min, and the amplitude of the following. So remember, for notation purposes, the textbook uses capital M to represent max. It uses little m to represent the minimum, and it uses A to represent the amplitude. And in general, we say that the amplitude is equal to the max minus the min over top of 2, or if you prefer, max minus min over 2. Either is fine. So we get these two graphs here. So the first one, we can see that we've got a max at 3. We've got a minimum at -6. So the amplitude will be 3 minus -6 over top of 3. 3 minus -6 is 9. Oh, not over top of 3, sorry, top of 2, which is going to be 4.5. And similarly, if we have a look at the letter B, we can see we've got a sinusoidal wave. This one goes all the way up to 7 and goes all the way down to appears to be -2. So this amplitude will be 7 minus -2 over top of 2, which is going to be 9 over 2, which is the same thing. As an addendum to this, it is worth noting that if you do the calculation this way, it is impossible to end up with an amplitude that is negative. That's not to say you can write equations for these that don't have a negative amplitude, but for our purposes, if you go ahead and calculate the amplitude via the max and the min, then you will always get a positive value. Okay, and the reason for that is because it has to do with where we start on this. And where I mean by where we start on this is with respect to a phase shift. So let's have a look. The phase shift of a periodic function is the amount by which the graph of a function is translated horizontally. So while it is correct to call a phase shift a horizontal translation, left or right, by some amount of units, it's worth noting that with respect to a periodic function, it's more correct to call it a phase shift. Okay, it's a better way to describe that than a horizontal translation. And you might have learned differently, but in this book, we use the letter P to denote the value of the shift. So for example, given f of theta equals sine of theta minus P is what it looks like. And so if you have g of theta is equal to sine of theta plus 2, that means we take the graph of sine theta and shift it left -2 units, or we go 2 units to the left. And so here, this red version happens to be the base function. And again, I'll just color this in. Again, the textbook doesn't use pi sometimes. It just uses decimals in radians. Just keep in mind, this is where we are. We're still in radians. And so I used an example here. So this value would be 2 pi. Here is 3 pi over 2. This is your pi value. This is pi over 2, and this is 0. And all we're saying is that we can see each of these values are dragged to left 2 units. So if I have a look at this value here, this is 6.28, and when we move it over 2 units, we end up getting a value of about 4.28, give or take. And so we take each of these and shift it over left 2 units. Concurrently, a positive p-value translates the graph right, or more technically speaking, is a phase shift 4 units to the right. You can also call this phase, like PS for phase shift, 4 with an arrow right, or you can write out the entire sentence, phase shift 4 units right. Either is okay. So if g of theta is equal to theta minus pi over 4, this will shift the graph of f of theta equals cos theta right pi over 4 units. And in this case, p equals pi over 4. This is very similar to how we analyze the x-intercepts with respect to polynomial functions. So suppose f of x was equal to x plus 3 and x minus 2. Then the x-intercepts would be the opposite of this. So we would flip the positive 3 to become negative 3 and flip the negative 2 to be positive 2. This is done the same way because we would essentially set the argument, meaning the inside portion of cos equal to 0. Pi minus pi over 4. Sorry, theta minus pi over 4 is equal to 0. We call it the argument for technical reasons, and sometimes I'll mention that, but just when I say that, I just mean the stuff that's affecting the angle itself. Okay, and so what does it mean to shift pi on 4? Well, this red function is the base graph, y equals cosine theta, and here's the normal graph. The reason why I made such a big deal about making sure that you committed that to memory back in lesson 10 was for these kind of occasions where I said, just make it a lot easier, just understand that these are what the values look like, because each of these individual concepts are not too onerous. It's just when they're combined together, can be a lot. Okay. Now, in this case, for this particular scale, we're going to go up by pi over 4, so that way it's easier for you to read. So we get pi over 4, pi over 2, 3 pi over 4, pi, and all we did was drag each unit pi over 4 to the right. If you want to think about this in terms of degrees, you could think about this as being cos of theta minus 45 degrees, like so, in which case all of these would be 45 degrees, or increments thereof. So we'd have 0, 45, 90, 135, 180, 225, 270, 315, 360, 405, and so forth. In which case you're dragging each of these units 45 degrees over to the right. Okay, and so you can do this in degrees or in radians, just make sure you're in the right units. Okay, so for example, my Desmos graph on the left, which I'm showing, is currently in radians, but if I click on the degrees button, I have to make sure to transform it over into degrees, or it's not going to be what I claim it to be. Okay, so let's continue on. So this is the toughest thing to do. So we're going to graph each sinusoidal function for one cycle. And we have 2 graphs to go through, and this is going to be the rest of class for us. So we're going to have a look at cos of theta minus pi over 2. So the most important things to consider. So as a consideration, we'll write it up in this graph. So as a consideration for graphing sinusoidal, or I should say graphing periodic. We haven't used the word sinusoidal, but it just refers to sine or cosine. So as a consideration for graphing periodic functions. Number 1, consider the phase shift. This will come tomorrow, but also the period. Again, the period doesn't exist yet. We know the period is going to be 2 pi. In the future, we're going to shrink that, but that's a topic for tomorrow. We're going to consider the phase shift of the function. Number 2, after that is where we worry about everything else. So this is like the amplitude, displacement, or I should say vertical displacement. So the question I get most from students is, how do I create a good like a good scale for my graphs? And this is the kind of stuff that we're talking about. So here, if we have to go right by pi over 2, this is the same thing as, remember, saying in degrees. This is y equals cos of theta minus 90 degrees. We want to make sure that we're actually able to easily graph what these things look like, or else that'll be quite tough to do. And so, since we're going to have pi over 2 units as going to be our phase shift, I want to make sure that my scale involves some sort of pi over 2 to make it easier for me to graph. So I'm going to ensure scale includes pi over 2 as an easy to read unit. Okay, with that out of the way, let's go ahead and graph this. Okay, so first things first, we know we have a max at 1 and we have a min at -1. The y-axis is not a big deal. Just make sure you give yourself plenty of space to account for the transformation that you care about. And so we need to go over pi over 2 to the right. So let's give ourselves plenty of space. So we'll call 1, 2, 3, 4 units. We'll call this pi over 2. The next one will be pi. Next one will be 3 pi over 2. Next one will be 2 pi. And the last one will be 5 pi over 2. If you want to think about this in terms of degrees, you can think about this as 90, 180, 270, 360, and 450. And again, you can always just convert these over into their radial equivalent if needed. Okay, so let's graph the base graph. So the base graph is going to be y equals cosine theta. So that's going to be a max, a 0, a min, a 0, and a max. So we can graph like so. Okay, so pretty sure that's what it is. So this is going to be y equals cosine of theta. And so when in terms of my steps, we always consider the phase shift, then we consider the amplitude and vertical displacement, and last thing is always sketch the base graph. Okay, it's like the easiest thing to do, to just make sure you do that because it makes it a lot easier. So for us, what do we have here? Well, we have a phase shift of pi on 2 units to the right, which means we're going to take each of these values and move them to the right pi over 2 units. So the point 0, 1 becomes pi on 2, 0. Sorry, pi on 2, 1. The point pi over 2 becomes the point pi, because again, we're going to the right pi over 2. The min here at -1 gets shifted over by pi over 2. At 3 pi over 2, that gets shifted over 2, pi over 2. And at 2 pi, when we add pi over 2, that becomes 5 pi over 2. And then from here, we can connect these all with a smooth curve. Okay, so all of these distances are going to be shifted over by pi on 2, right? And we just had to make considerations to ensure that we had an easy scale to help us translate by. So in this case, if I see like a phase shift of pi over 2 or pi over 4, then I want to make sure my scale has an easy pi over 4. In this case, suppose that this with cosine theta had to be a pi over 4, then halfway between pi over 2 and 0 would be a pi over 4 scale, and that would be easy for me to do. Okay, so you want to have a nice, easy scale to account for the phase shift, because these things can be quite messy otherwise. So this is when working exact solutions. So these are exact values. Exact values involve some kind of pi. Now, we can also have the situation where we're going to be moving to some direction by a unit. So here, the unit's going to be 1. So we're going to move 1 unit to the right. And if we're moving 1 unit to the right, then we want to make sure that our scale goes up by 1, so that, or somehow go up by 1 so it's easy to read. So something that I might not want to do is I probably don't want to do this. So if I try to proceed in the normal way, pi over 2, move over 1, 2, 1, 2. Let's give myself a little bit more space. Let's at least be a bit more polite. So we'll go 1, 2, 3. We'll call this one pi over 2. This is pi. This is 3 pi over 2. 1, 2, 3, 4. And this is 2 pi. So this is not going to be a good scale for me. Okay, so here we have a phase shift of 1 unit to the right. But where is 1 on this graph? It's kind of hard to tell, right? So here, this value is going to be 1.57. It's going to be 3.14. This is going to be 3 pi, 4.71. And this is going to be 6.28. And so somehow I have to move the value over 1. But we don't know where 1 is exactly on this graph, right? So I guess 1 is going to be a little bit closer to pi on 2. So it's not quite halfway between 0 and, yeah. So you can see what I mean? Like, so going up by pi doesn't really make any sense for us in this graph. It's going to be quite difficult for us to read. So instead, since we are making a horizontal translation of just 1 unit to the right, we actually should convert these over into numerical numbers instead. So let's call, and we're going to make it easy for us to understand. So note here, we got to be careful because we saw from earlier that when we're having a look at theta and sine theta, we know that the values for theta we're going to choose are going to be 0, 1.57, 3.14, 4.71, and 6.28. And those are going to correspond to 0, 1, 0, -1, 0. So we want to make sure we're easily able to sketch out those decimal values, right? We saw this earlier when it talked about a phase shift, right? So you can see here that when they were going up by some number, they had to just make a scale and then try their best with plotting the pi values. So here, I suppose, let's call this 1. We'll call this 2, 3, 4, 5, 6, and 7. We don't quite have enough space. I would have liked to leave more space, but there's just not enough values here. And so now we're going to graph what this looks like. So here, 0, 0, that goes first. There it is here. We'll put 1 up there and below. Maybe we should label it a more clear color to make sure we can easily read it. Okay. So 0, 0 is there. 1.57 is like just above halfway between 1 and 2. So that'll be the max. 3.14 is just a bit after 3. So that's going to be the next value. 4.7, that's like halfway between, or 3/4 of the way between 4 and 5, but just before it. So we're going to put it, like, I suppose, around here. And the last one is 6.28. So that's like about halfway again between, or 1/4 of the way between 6 and 7. And so then we can connect these with a smooth curve. I got to redo that curve, wasn't my best. And we'll just color in these points nice and large so that way it's clear what these are. Okay, so you can see already a lot of work. So far I spent 9 minutes trying to describe how I want to draw the scale of these things. So doing these by hand can be quite time consuming. So that's why it's important to choose a good scale in advance so it's less work. Okay, so this green curve is going to be y is equal to sine theta. Now, the easy part is that we need to have a phase shift of 1 unit to the right. Well, that's pretty easy now because we take each of our 5 units and we move it over 1 unit to the right. So this 1.57 number becomes 2.57. It's about there. 3.14 becomes 4.14. 4.71 becomes 5.71. And 6.28 becomes 7.28. And so we can see this will be the corresponding phase shift function. Oh, we should that curve the other way. So this will be y is equal to sine of theta minus 1. And we're only doing a right side phase shift just because that's what my graph is. A left side phase shift would be done identically the same way. We just have to account for negative values. Okay. So in terms of a table of values for these, the y values would still stay the same. It'd be 0, 1, 0, negative 1, 0. And this would be theta and sine of theta minus 1. So it is, instead of 0, it would be 1. Instead of 1.57, it's 2.57. 3.14 becomes 4.14. 4.71 becomes 5.71. And 6.28 becomes 7.28. And just to reiterate these points, that's why I said the main thing we want to do is to consider the phase shift and later the period of the function, because that's going to be the important part with respect to the scale for a graph and where we're going to spend most of our time. All right. With that, that's most of lesson 11. On the lesson of next time, we're going to combine some transformations together. And in fact, that'll be the first question for us. But for now, as always, if you have any questions, please feel free to email me. And we'll see all of you next time. Goodbye for now.